Lesson: Overfitting and Underfitting, Detection and Mitigation Strategies. Overfitting and underfitting are two critical challenges encountered in the development and deployment of machine learning models. Understanding these phenomena and how to effectively detect and mitigate them is essential for professionals seeking certification in AI scripting and machine learning principles. Overfitting occurs when a model learns both the underlying patterns and the noise in the training data, leading to excellent performance on the training set but poor generalization to unseen data. Conversely, underfitting arises when a model is too simplistic to capture the underlying structure of the data, resulting in poor performance on both the training and unseen data. Detection of overfitting and underfitting requires careful analysis of model performance metrics. One of the most straightforward methods is to evaluate the model's performance on both the training and validation datasets. If a model performs significantly better on the training data than on the validation data, it is likely overfitting. Conversely, if a model performs poorly on both datasets, it is likely underfitting. Cross-validation techniques, such as k-fold cross-validation, are effective in assessing model performance and detecting these issues. By partitioning the data into k subsets and training the model k times, each time using a different subset as the validation set, one can obtain a robust estimate of the model's generalization ability. To mitigate overfitting, several strategies can be employed. Regularization techniques, such as L1 and L2 regularization, add a penalty term to the loss function to discourage overly complex models. These techniques are particularly effective in linear models and can be easily implemented using popular machine learning libraries such as scikit-learn. Another strategy is to use dropout, a technique commonly applied in training neural networks. Dropout randomly sets a fraction of the activations in a layer to 0 during training, which helps prevent the network from becoming overly reliant on any single feature. This is readily available in deep learning frameworks like TensorFlow and PyTorch. Early stopping is another method to prevent overfitting, where the training process is halted once the performance on a validation set starts to degrade. This approach can be implemented by monitoring the validation loss during training and stopping when it begins to increase. Data augmentation, which involves creating new training examples through transformations such as rotation, scaling, and flipping, can also help mitigate overfitting by increasing the diversity of the training data. Addressing underfitting typically involves increasing the model complexity. This can be done by adding more features to the model, increasing the size of the model, or using a more sophisticated algorithm. For instance, decision trees can be expanded by increasing the maximum depth or number of leaves. However, care must be taken to avoid transitioning from underfitting to overfitting by monitoring the model's performance on validation data. Feature engineering plays a significant role in mitigating both overfitting and underfitting. By carefully selecting and transforming variables, one can improve model accuracy. Techniques such as principal component analysis can be used to reduce dimensionality while preserving important information, thereby simplifying the model and reducing the risk of overfitting. Feature selection methods can also be employed to identify the most relevant features, removing those that contribute noise or redundancy. Hyperparameter tuning is another essential aspect of optimizing model performance and addressing overfitting and underfitting. Tools such as grid search and random search allow for systematic exploration of hyperparameter spaces to identify the best configuration for a given model and dataset. More advanced techniques like Bayesian optimization can provide more efficient means of tuning hyperparameters by using probabilistic models to guide the search process. Real-world applications and case studies provide valuable insights into the practical challenges and solutions associated with overfitting and underfitting. For example, in a study involving the prediction of housing prices, researchers found that a simplistic linear regression model underfit the data, failing to capture complex relationships between features. By incorporating polynomial features and applying L2 regularization, they were able to significantly improve the model's performance. In another case, a neural network trained for image classification exhibited overfitting, performing exceptionally well on the training set but poorly on the test set. By implementing dropout and data augmentation, the researchers were able to enhance the model's generalization capability. Statistics further illustrate the impact of these strategies. For instance, studies have shown that applying dropout in neural networks can reduce test error rates by up to 50% in some scenarios, underscoring its effectiveness in combating overfitting. Similarly, data augmentation has been shown to improve the accuracy of image classification models by more than 10% across various datasets. In conclusion, the detection and mitigation of overfitting and underfitting are fundamental skills for professionals in machine learning. By employing strategies such as regularization, dropout, early stopping, and data augmentation, one can effectively address overfitting and enhance a model's ability to generalize to new data. Conversely, increasing model complexity and leveraging feature engineering can help overcome underfitting. Hyperparameter tuning further optimizes model performance by identifying the best configuration for a given problem. Through practical tools and frameworks such as scikit-learn, TensorFlow, and PyTorch, these concepts can be readily applied to real-world challenges, thereby enhancing the proficiency of professionals pursuing the CompTIA AI Scripting Plus certification.